In this video, we're going to discuss Voltaic cells. So in previous videos, we discussed redox reactions, where elements exchanged electrons, something was oxidized, something was reduced. Generally, if you do a redox reaction just in solution, it heats up the solution. It gives off a tremendous amount of heat. There's a lot of work that could be harnessed from a redox reaction. The transfer of electron, if you use a device that's correctly designed for it, can harness that flow of electrons to power devices. This is how batteries work, and voltaic cells are generally what we think of as batteries. So let's dive into the construction of a device that allows us to harness that transfer of electrons from a spontaneous redox reaction. Simple lab-sized scale, we could have a beaker with some liquids. We could have a piece of metal dipped into it. This could be hooked up to a device, some kind of electronics, some kind of measuring device, something that's going to make use of electron flow. And then this hooked into another piece of metal that's in another beaker with some solution. And what we're going to make of these is we're going to make one of these zinc metal, and the other is going to be copper metal. And the solution is going to have a solution of zinc 2+ and some counterion, we'll say sulfate. On the copper side, we're going to have a solution of copper 2+ and some counterion. Again, we'll go with sulfate. Keep things consistent. There's one last component that's needed, and that is usually a little tube filled with gel we call the salt bridge. This is some inert set of ions. This could be potassium nitrate. Sometimes this could be sodium sulfate. Depends on exactly what cell you're building and what various ions might react with things. But this is a semi-porous gel-like material with ions that can move around. And we'll see why we need those in a second. What we have here is a device that is going to perform the reaction of breaking zinc off. So bit by bit, zinc is going to break off and go into solution. Why is it going to do that? Well, copper is going to stick onto the copper. So what's going to happen on this device is a reaction of zinc solid plus copper 2+ aqueous is going to form zinc 2+ aqueous and copper solid. Now we could do this in one container. If I had a bunch of copper 2+ in a container and I dropped a bar of zinc in, what would happen is that the copper ions would start to stick to the zinc and they'd pull electrons. Zinc atoms that had been in the bar would lose those electrons and dissolve away into solution. Bit by bit over time, we would plate copper out on the bar. We'd make little holes in the bar where the zinc left. And eventually what will happen is you'll have a zinc bar with a bunch of copper on it. This is actually one way you can plate a piece of metal. You can dip a lesser metal into a solution of something that wants electrons more, and it will begin to coat the surface of that bar of metal. It does it by stealing electrons from some of the atoms in that bar and kicking them out into solution. Well, this doesn't allow us to capture the flow of electrons, though. This happens all in one spot. There's no way to harness that. Our voltaic cell lets us do the same reaction, but by separating the two halves into different components. The electrons are forced to flow through our device to make it to the copper. At the atomic level, if you kind of think about it, I've got a bunch of copper atoms on the bar. So yay, a bunch of copper. And I've got a bunch of copper 2+s floating around solution. Well, the electrons are all around the metals. They're in distributed orbitals. D orbitals are quite far away. And so as one of these ions kind of comes up and sticks, well, there's no reason those electrons can't just flow out onto it. And so you get a flow of electrons out here, turning this not into 2+, but just into regular copper now. Well, those electrons had to come from somewhere. Initially, it's just neighboring electrons. The sea of electrons in a metal is very loose. They can flow around, but they have to flow down, they have to flow, and they keep flowing in. And what we see is as these ones flow out to the copper ions, electrons have to move in to replace them, and they'll end up moving in from the zinc. At the atomic level over here, I have a bunch of zinc atoms, and the electrons are jostling all over, and some of them just kind of leave to go up. As a result, electrons that would have been out here on this last one end up shifting further up to kind of replace that gap, meaning this zinc no longer has those 2 electrons. It now becomes 2+, and it can break free and drift off into its solution. Effectively, we've pulled electrons off of the zinc bar, moved them through the whole device to put them onto a copper ion, touching the surface of our copper metal. This still allows us to perform the same reaction, but it has to travel through the wire connecting the systems. As a result, we can harness that flow of electrons. This is the general idea of the Voltaic cell. A few terms we've got. You have your anode. Anode is where the oxidation occurs. In this case, that's over here at our zinc. And there's a cathode, which is where your reduction occurs. That's over here at our copper. This setup of a piece of metal with a solution of its ion, and then another piece of metal with a solution of its ion being connected, allows the electrons to flow from the more oxidizable metal over to the metal solution where the ions are more reducible. Why this goes from zinc to copper, we'll explain when we get into cell potentials. However, at this point, this is simply the general layout. You could put any 2 metals in here, and as long as one is easier to oxidize than the other, you're going to favor your electrons going in one direction. As this occurs, let's focus on that salt bridge for a minute. As my coppers that originally match the number of sulfates I have start to stick to the metal, some of the positives in solution go away, leaving just sulfates with no cation to match them. As our coppers stick to the surface and gain electrons, I obtain a charge imbalance in my solution. And over here in the zinc, where one of these just breaks off and becomes a zinc 2+, we start building up positives. Now between the 2 cells, they may balance out. For every copper that leaves a sulfate, a zinc is produced on the other side. But they're in different containers. They are much too far away to interact. This is where the salt bridge comes in handy. Your salt bridge is effectively just a large ion source. You have a lot of sodium ions float in it. You have a lot of sulfate ions in it. And as the solutions change, you will have these ions start to flow to balance out that charge. You'll have sulfates flow over to match with the zinc. You will have sodiums flow over to match with the sulfates. By having this salt bridge able to transfer ions across, you're able to maintain your charge balances. If you don't have the salt bridge, very rapidly any electron transfer shuts down. Creating a charge imbalance in your solution is immensely disfavored. You really can't have very much charge that's not balanced within a given area. And so this salt bridge is required in order to connect this device to balance the charges as the redox and oxidation occurs.